Well, yep. I didn't have my usual tunes today, so sorry about that. I have a little problem with my Rodecaster Pro mixer where I usually queue up a few rockin' tunes to start the whole thing with, but not today. So there we go. Um, let me just get myself into gear here and make sure I've got all my things running, ready to go. Yeah, that's it. Good. Welcome everyone to another Toolbox Tech Talk here Sunday, coming to you from the Smart Energy Lab in the Yarra Valley, not far from Melbourne. So great to see there's people joining us from all over the place. G'day, Scotty from Pakenham. Feel free to shout out in the chat, say where you're listening to this from. I'm always excited to know how far my reach is. So let's see who can be the farthest away from little old me in the Yarra Valley. So today is all about overcurrent and isolation, overcurrent protection and isolation for battery systems. So we'll dive into that in a minute. But as usual, I just like to thank a few people. I've had some great emails come in during the week with some questions. I haven't got to them all yet. It's been a bit of a busy week, but I really appreciate them. So I'll pop that in the chat just to get you ready for it. So Glenn at SolarQuip, here you go. If you email me on that address, that would be great. Kalbari, okay, yep. Cool. That's where Scott's coming from, the other Scott. We've got a couple of Scots there. And Gian from Sydney, g'day. And Peter from beautiful Cavity Coast in New Zealand. My hometown, my homeland. I actually grew up in Lower Hutt, so not far from the Cavity Coast. G'day from Rotorua. Whoa, Rotorua. Can it be a bit like that? No? And Perth, wow, yeah, you're watching this a little bit earlier in the day. And that's Richard. G'day, Richard from Perth. And Dowger from North Coast of New South Wales. Wow, we've got a great spread there. None of the international ones yet, but we'll see. Yeah, so just a usual thing where I'm promoting some of the online learning activities that you can engage in. So joining the Smart Energy Council's Smart Installer program, that's a great option for getting access to the relevant standards. It's free to join. You get a free copy of 4777 Part 1, the inverter standard, the 2024 edition, which is now mandatory in Australia. One day in New Zealand. And if for another $99 plus GST, you can get the whole bundle of 9 standards. Now, a few people quibbled that how come last year they were free? Basically, a bunch of companies, bless them, paid the fee for you for a whole year and made access to the standards for free. So if you didn't grab them last year, you kind of missed out on that free deal. So $99 is bloody cheap for 9 standards, certainly in Australia where they're $200 or $300 each. So yeah, that's really good. And the lucky folk over in Kiwi land there, members of the Electrical Workers Registration Board, get them for free, as they should do, because it's your safety advice for your industry. Also, with the Smart Installer program, you can gain CPD points. So here in Australia, we have to have 100 CPD points to maintain our accreditation with SAA. So there's over 170 CPT points available through online content. So don't leave it to the last moment. When your accreditation's about to expire, just clock up those points early. And then there's the Solar Cutters. Solar Cutters, who have been a great supporter of this channel. I'll actually see if I can bring up their page. Here we go. So that's Solar Cutters there. And they are a non-government organisation, basically a member-based support group for people in the solar and battery storage industry. And they're a great organisation, run a lot of workshops, and the roadshow at the moment is going all around Australia. I'm not sure where they're up to yet, but Bendigo, Hobart, Penrith, Melbourne, Cairns, Newcastle, Byron Bay, Adelaide, Geelong, Canberra, Townsville, Perth, Brisbane and Albury. That's pretty good coverage. And lastly, there's the big expo coming up, the Smart Energy Expo on the 9th and 10th of April. Fingers crossed we don't have an election right in the middle of all that, but there's a good chance we might. So there you go. So that's kind of the things that I just want to remind you about. Now, let me just get my Prezzo ready. Where are we? There it is. Okay, so we're going to be talking all about batteries and battery systems. Now, little define my terms here. A BESS, B-E-S-S, is a battery energy storage system, which includes the PCE. So something that's an all-in-one solution. Something that has for example, an inverter and a battery in a box. So something like the Tesla Powerwall 2 is a BESS. In fact, Tesla Powerwall 3 is a BESS. It's got the PCE for solar and PCE for battery. It's basically all in one thing. So there you go. That's the a BESS. But today we're talking more specifically about battery systems. So the DC side, we're not so much focusing on an all-in-one solution, but where you have a separate battery and you connect it via installation wiring to PCE. So I'm just checking down here. Oh, g'day, Mark. Hey, shout out to Mark Kavanagh there, MC Electrical. He's got a great channel on YouTube too. You should check him out. And g'day, Arthur from Darwin. Yep. Steamy Darwin, eh? So, yeah, we're specifically talking about battery systems. And because you are installing cables between a battery and PCE. Now, by the way, PCE, power conversion equipment, is just a generic term for anything that modifies frequency, voltage, or current. So an inverter is PCE, an MPPT is PCE. You could even say that a VSD drive is PCE, anything that modifies voltage, frequency, or current. So we'll see a couple of those examples. Oh, g'day Garth from Harvey Bay, sunny Harvey Bay there, or maybe stormy. I don't know what it's like today. Can be pretty exciting up that way. Wow, we've got a great turnout. Obviously, you guys like to talk about batteries. So let's jump into my prezzo. So here we go. So first up, we're going to be talking about parallel systems. Now, these are clippings from the battery standard AS/NZS 5139, so published in 2019. We are actually updating it at the moment on Standards Committee, so we're going through a review process to try and iron out some of the poorly phrased terms, you could say. So this was a brand new standard. It wasn't replacing an existing standard, and we had to rush it really when we produced it. There was a lot of pressure to get it out, and it did have a few quirks. So we're in the process of fixing those now. So I'll update you once that's public comments out, so you can have a read of it. So yeah, when we're talking about parallel battery systems, I just want to focus on the highlighted section there in yellow. For a BESS consisting of 2 or more pre-assembled battery systems. Now, as soon as you see the words pre-assembled, you know that you're in sections 4 or 5, because 4 or 5, 4 is for a BESS that's pre-assembled, and section 5 is for a battery system that's pre-assembled, and it has to comply with what's known as the best practice guide for energy storage systems. The best practice guide is not a standard, it's kind of a quasi-product standard. I've probably mentioned this many times, but because we don't have product standards for residential energy storage systems, we actually had to kind of cobble together something to indicate a high level of confidence in the safety of a battery system. And so the best practice guide refers to other, both international and national standards by one of 4 different methods. And you choose, and when I say you, the manufacturer. As an installer or designer, you don't even need to read the best practice guide, you just need to know that it exists and that compliance to it is required if you have a Section 5 battery system or a Section 4 BESS. The words pre-assembled too can be confusing. It doesn't mean it is all in one box to start with. It could be, it's like an IKEA kit. Everything is in the box, you assemble it on site with no on-site manufacturing. That's what pre-assembled means. So just because you've got some cells that some battery modules that you clip together and a PCE that you clump on top and turn it all on, that is actually pre-assembled if it's designed as a whole. And we'll talk about what the implications of that are. So to carry on here, pre-assembled battery systems connected in parallel. So you've got more than one battery system. So let's think of say a 19-inch rack-mounted battery. You've got more than one of them. See those ones on the side of that picture there? Me looking a bit curious. Those are Power Plus Energy 48-volt nominal battery modules. Each one's around about, I think, 3.8 kilowatt hours. I think they've upgraded that to 4 now. And they are all in parallel. So they all connect onto a bus bar at the rear. So the output cable from each battery system to the point where the parallel battery system is connected, i.e. At the PCE or a bus bar, shall have equal cable length. Now, I've got some little drawings to explain this one. It's surprising that we've got a shell here. When I say surprising, normally shells are reserved for safety, and this is kind of a performance consideration. So let me just get my drawing in place here. Where's my overhead drawing? There it is. Okay, so you should be seeing my little hand sketch that I just did. All right, so I'll run you through this. Let me get my favourite pointer pen. Where is it? Go. Look at that. One of these little gifts you get. Look, from Power Plus. It's a ruler, metric and imperial. It's a pen, and it's a level. That's pretty cool, eh? Anyway, what I want to show is wrong and right when you parallel battery systems. Now, it's very easy to think I've got 3 batteries here, A, B, C, and I'm just going to parallel them all onto a common point. Or let's say those little dots are all a common point. But when you measure the cables, they're all different lengths. The battery A is very close to the commoning point, whereas the worst case is battery C is a long way from the commoning point. And what you're getting is voltage drop under load. So voltage drop in this example here, let's say at 100 amps, might get half a volt. From battery A to the commoning point, 0.75 for B, and a whole 1 volt for C. Now, why is this a problem? Well, the PCE, which is trying to manage these batteries, which is connected up here, can only see the voltage at this point. And so if it's trying to reach a target voltage of, say, for a lithium-ion battery, it might be 56 point something, 56.2, it depends on the chemistry, of course, volts, and it's pumping 100 amps in, it can't see that actually the voltage drop here is quite severe. So this battery is not getting that target voltage. So effectively, this one gets charged first, this one doesn't get fully charged, and this one's quite a bit down. So that is pretty important. So what you should be doing is maintaining all of your cables the same length. Now, I've shown a little curly-whirly here. Sometimes you just have to cut all your cables and find ways of wrapping them so that they all sit nicely in your ducting or cable support system. But basically, all of those cables are the same length now, all of the positives, all the negatives, and therefore the voltage drops are all identical. Yep. Oh yeah, it's also a screwdriver? Really? Someone just told me this is a screwdriver. I can't see where the screwdriver is. Really? Don't tell me this is a screwdriver, Scotty. I'll get in trouble taking it on an aeroplane. They're always confiscating my nice cool toys off me. But anyway, apparently it's a screwdriver. So there you go. So that's the correct way. Keep all your cables the same length, and it is actually a shell in the standard. So there you go, surprisingly. Okay, so let's go back to my slide and we'll go to the next point. Okay, so this is parallel battery systems. I'm being distracted. Unscrew the cap. Really? Oh, whoa, that's sneaky. Wow. Let me bring that up for you. It's a little screwdriver hidden in there. I wonder if airport security would notice that one. Don't tell me there's a weapon in here as well. Wow. Thank you, Scotty. I just didn't know that. I should have read the instructions. All right, so back to isolation. Switching over to isolation now. So we'll be talking about overcurrent, system cable design, and isolation, sort of back and forth a bit. So isolation, the isolation devices shall be readily accessible. Now, the term readily accessible is defined in our wiring rules, AS NZS 3000, and it means without disassembly or removal of parts. So the idea of an accessible switch or isolator in this case is so that the non-authorized workers can switch stuff off. They don't need to have a special tool to get to it. So a main switch, for instance, is readily accessible. And I like to kind of just remind myself the difference between accessible and available. So accessible is like you can roll up to it in a wheelchair. That's accessible and operate that switch. You don't have to have a special tool. But readily available is for maintenance and repair. So we need an accessible isolation device. So it can't be embedded inside the unit that you need to unscrew to get to. it goes on in the second paragraph where the cables connecting to the pre-assembled battery system to the PCE, so from the battery system to the PCE, are greater than 2 meters. So this is 2 meter rule. In fact, the wording changes in the standard. One place it says 2 meters of cable length, and somewhere else it says 2 meters of distance. There you go. There's already a problem. They haven't been consistent with the wording, but let's just go with 2 meters of cable in length. An isolating device shall be installed at both the pre-assembled battery system and the PCE. So in the pictures down below here, and I can't use my mouse because it's on the screen, but if you look at the picture on the left, there's our battery system, but the MPPT is 6 meters away, and so it needs to have its own isolator adjacent to it. So it's got a DC isolator right next to the PCE, and of course the battery system has its own means of isolation. So there you go, 2 meter rule. So try and keep your battery close to your PCE, and you only need one isolation point. But if it's more than 2 meters, you're going to need 2 isolation points. By the way, as I go and you have some queries, just type them into the chat. There is about a 10 or 20 second delay between when you see me talking and when I actually get to read your text. So don't delay, just type it in there if you've got a question. And can anyone give me feedback on the stream quality? Last week I had a lot of technical problems and it was driving me nuts. I've got dual WAN, so dual wide area network connections, one through Starlink, one through an Optus 4G, and Starlink was a bit flaky, and I usually use Optus, but Optus was down because they're upgrading the transmitters. So we're back in action with quality, hopefully, streaming. So yeah, if it's all good, let me know. And going on to our next point, thank you, Jian. He says, very good. That's great to hear. Now let's look at the location of with a BESS with multiple PCE. So where you've got, and it's saying BESS here. So when a BESS includes multiple PCE, power conversion equipment, such as a solar charge controller and an inverter, or multiple inverters, a separate isolation device shall be installed adjacent to each PCE. Now, I'm going to have to fess up here. The system that you probably see a few pictures of here was installed before 5139 was published. And so we didn't meet this requirement. In fact, as soon as we do any modification to it, we will. But we should, there's 6 inverters in this system. We should have actually had an isolator next to each inverter and also the MPPT. What we did have is a large amount of string overcurrent protection, battery overcurrent protection for all of the 6 inverters separately, but not individual isolators. So yes, if you've got multiple inverters, each one of those needs to have a means of isolation. The premise really in our standard is don't work live. So when you're working on equipment, you should be able to reach the means of isolation, not kind of have to wander around to another room and hope it's switched off. Basic safety. Okay, gee, everyone's saying the stream quality is really good. That's great to hear. And lucky Scott, he's on 5G. Volume seems a tad low. Okay, because I have had to switch my audio around because my mixer kind of carked it this morning. Maybe I'll just bear with me if audio is a bit low. I'll just pump it up a little bit. And let me see if I can do this real quick. 1, 2, 3. Okay, how's that? Is that a little bit punchier? Let me know in the comments. Okay, so here we go. Got the audio volume turned up a little bit higher. I should have been looking at my VU meters. I can see it's in the good zone now. All right, so back to my Prezzo. Now this is kind of a long and wordy clipping from 5139. Types of cable. So I better define a few terms here. DVC, decisive voltage classifications, comes from IEC 6109 part 1, which is the standard for PCE connected to PV array. Thanks Garth to telling me the audio is better, and Mark, yep. It's always a problem when you've got your own volume control for your headphones, but you don't know what the audience is hearing. I just should have looked at the VU meters. Shepsy, it was definitely my problem, not yours. So, yeah, coming back to DVCs, decisive voltage classifications are a move away from our sort of more conventional in 3000s wording of LV and ELV. So in AS/NZS 3000, we refer to extra low voltage as below 120 volts DC, and low voltage is over 120 volts DC. We'll ignore the AC side because we're talking about batteries here. And, we've got a question here. Arthur says, what if the PC manufacturer forbid disconnecting the minus between the inverters? Okay, so manufacturers' recommendations must be followed if they're additional to the requirements of our safety standards, but they cannot take away the requirements of our safety standards. So it's in Australia and New Zealand, under all our standards for battery systems, we always require double pole isolation. So there's plenty of products. In fact, we're a bit odd like that. Most of the world is quite happy with a single pole isolation. And so there'll be a lot of products on the market that might just have isolation on the positive, for instance, and a common neutral, so negative. But that's not compliant under the Australian New Zealand rules. So, if the manufacturer forbids it, then you can't use the product. So, yeah, it's a bit of a problem. And it's actually to do with safety because certainly with inverters that are non-galvanically isolated, which is basically all grid tie inverters these days are transformerless, you can actually have earth faults through either pathway. So you can have earth faults through the positive or through the negative conductor. So you need to be able to isolate both of them. So it's actually a higher level of safety. Coming back to the slide here, so DVC-A is less than 60 volts DC. In fact, the wording is must not exceed 60 volts for more than 2 seconds under any operating, 0.2 of a second under any operating conditions. So it's very, very limited to 60 volts, DVC-A. And so most nominal 48 volt lithium ion batteries will be within that DVC-A range. It's when you're looking at some other esoteric battery types or even good old flooded lead acid. Flooded lead acid often would go over 60 volts for a 48 volt bank in equalization. So they become DVC-B. So DVC-B is between 60 and 120 volts DC, and DVC-C is above 120. Now, in our battery standard, we consider anything over 60 volts, DVC-B or C, is equivalent, this is the wording in 5139, as equivalent to an LV installation as defined by 3000. So going over 60 volts, you basically got a level of hazard that's expected to be the same as an LV installation, and therefore your requirements for protection step up. Just seeing a bit of chat here. Shepsy says, Glenn, around AC isolation, there was some greyness around groups of inverters, example 3, multi-mode inverters creating 3-phase where inverters are spread across several meters was generally. Yes, so that's exactly the situation we have. And as I said, if there are distances greater than 2 meters from the battery or any one of those inverters, you need to have isolation adjacent to each one of them. And if you've got, and additionally, which kind of overrules that clause, if you've got more than one PCE, each one needs its own isolation. So yeah, 3-phase system made up of 3 single-phase inverters, isolation for each of them. Yeah, so lots of flooded lead acid absorb at 60 volts, that's right. 61, well, it just depends on temperature too. So, you know, when they're hot, they get a little bit higher. So coming back to this clause that you're probably staring at for a while here, I'll just reiterate it. So the cable from the battery system to the PCE shall be double insulated if the battery system's maximum voltage exceeds DVC-A. All right, so if you've got a battery over 60 volts, it must have double insulated cables. But if you've got a, down the bottom there it says, it's double insulated for DVC-A battery systems connected to non-separated PCE. Now, when I said non-separated, that means non-galvanically isolated, which is pretty much the case for just about all charge controllers. There's only very few that have galvanic isolation. I know that the Victron RS450 does, the AERL MPPTs have galvanic isolation, but it's a pretty rare one. Oh, and Schneider as well. I can only think of 3. Schneider 600/80 unit. So it's pretty rare. So effectively, you're going to have double insulated cables when the PCE side is above DVCA. Now, I think I've got a little drawing of this. Where are we? Where's my drawing? And okay, here's my little drawing. So bring it out there a little bit. So let's say we have a 48-volt battery system, and it's DVCA, so it's a lithium-ion battery. It doesn't get over 60 volts. We need double insulated cables between the battery system and the overcurrent protection device. So even though it's DVCA, we still need double insulated cables at that point. Now, if the MPPT, in this case, or more technically the PCE, is not galvanically isolated, therefore it's non-separated, then the highest voltage present, which is likely to be the PV array in this case, is over 60 volts, then this cable needs to be double insulated as well. So the concept there is that because there isn't galvanic isolation between the PV and the battery side and the PV side, you can actually have the PV voltage under fault conditions appear on this cable. So I've also shown the 2 meter rule here. So as long as there's less than 2 meters between the PCE and the battery, we only need 1 point of isolation at the battery system. But if it's greater than 2 meters, we're going to need isolation at both the PCE and at the battery. So that 2 meter rule kicks in. So that's covering off on types of cables. Okay, and I can see a little bit of chat about the Victron RS being galvanically isolated. There is kind of a problem with this whole concept of galvanic isolation. Is how do you know? You might think, oh, it's going to be written on the side. Actually, it's not a labeling requirement, and it's a real flaw in the label requirements in IEC 62109. 62109 requires certain mandatory labeling on PCE, such as maximum voltage, maximum current, short circuit rating, but it doesn't require topology. So topology would be whether it's separated or non-separated. And so you're falling back on the manufacturer telling you. And I know certainly in New Zealand, there's been quite a bit of discussion about this, which is how do you know if an inverter that's connected to a DVCA battery, which is therefore below 60 volts, is not a 60 volt battery or less connected to a multi-mode inverter, such as a hybrid inverter or an off-grid inverter, whether that inverter is galvanically isolated. Because if it's not, you can't use it. That's the wording in 4509 Part 1, the standard for standalone power systems. It's also in 4777 Part 1, which is you must have galvanic isolation for DVCA battery systems connected to PCE. So if it's not, then you can't use it because you've got a hazardous potential at the battery terminals. I mean, we have actually had a fatality in Queensland that I know of from someone was putting a little 12-volt inverter on their vehicle, and there was a fault in that product which led to AC appearing on the battery terminals, and they got electrocuted. So that's one of the reasons why we require that galvanic isolation on DVCA systems connected to PCE. Thanks, Arthur, for pointing out the data sheet shows that the galvanic isolation exists. But like I said, it's only the manufacturer telling you that. It's not mandated in the labeling. And I jokingly say there's a simple way to test this, by the way. So if a manufacturer says, yes, it's galvanically isolated, then just try connecting a earth to the positive or negative terminal of the battery and see if the inverter blows up. If it blows up, it wasn't galvanically isolated. Yeah, a brave person to do that. In fact, I've accidentally done it myself. And the smoke did come out. Wow, there's some good chat going on there. I can see between Arthur and Shepsy about galvanic isolation. Yeah. Okay, so now we're going to get on to current carrying capacity. So let me bring that one up. Current carrying capacity. Okay, so the current carrying capacity of the pre-assembled battery system's cable to the overcurrent protection device. So it's kind of like you've got an overcurrent protection external to the battery system, but there's going to be a cable from the battery system to that device. And it must be rated for the maximum current rating of the battery system and the short circuit current and duration of the battery system. So, you know, under fault condition, before the overcurrent protection device gets a chance to trip, that cable's got to be sustain that fault current. And that's basic premise of cable selection. So you would select your overcurrent protection device and then select a cable that is adequately protected by that device. G'day, Jason from Perth. Nice to have you join us. So now I did actually draw something. Let's see if I've got it handy. Just explaining this one. And I think, oh yeah, it kind of relates to parallel battery systems as well. Maybe I'm going on a slightly different tack here, but I did want to talk about this. Okay, so what you're looking at here is a battery system where all of the battery modules are in parallel. And can I zoom in anymore? I can't zoom anymore. There we go. Sorry, it's a little bit small. Let's see if I can make it a little bit bigger. Oh, it just brings me into the picture. There you go. So let's say these are 19-inch rack-mounted batteries, and they've got these double terminals, 2 positives and 2 negatives on each one, and they have little linking cables, so you can effectively parallel all of the battery modules together. Now, I was trying to find a picture that was on the Solar Cutters page of this, and people were querying it. When you think about it, the output is from the last one in the stack, and each one of these battery modules can source 100 amps, but it's sourcing it into the next battery module. It's sourcing it in parallel to its output terminals. So we have 100 amps through this cable, we have 200 amps through that cable. This is under full power, 300 amps through that cable, 400 amps through that cable, and 500 amps through that cable. And what do you know? The ones that are supplied with the units are a little bits of 35mm cable with some quick connectors on them. And so really the only one that was rated correctly was the first one for 100 amps. If I look at the tables in 3008, which you can use for DC sizing as well, even it says so in the preface. And by the way, we're updating 3008 to have some specific DC tables. But the way to look at it is there's always less loss in a DC cable compared to AC. You don't have skin effect or proximity effect. So if you can meet the requirements for AC cable, also AC current, you'll easily shoe in for DC. So 35mm cable would be adequate here, but really we need to step up to 95mm cable for the next battery. Then we get up to 300 amps. On this one, I'm going to have to use pairs of 240s and going to ditto all through to the last one. So suddenly I've got a huge cables coming off this system because the currents are adding together in parallel. And that little link cable is not good enough. Now you might say, hang on, Glenn, there's overcurrent protection on these batteries. That's right. There's a 125 amp circuit breaker in each one of these, or 100 amp even. It still means 100 amps goes in here, and then 100 amps is coming out of each of these. And these terminals are often on the output of that overcurrent protection device, not on the input to it. So there you go. But, and I see a comment from Shepsy, and I think I'm going to explain this one, Shepsy, which is, I'll go to it, here we go. But there is a solution to this, and it's where you have parallel battery systems which are a pre-assembled battery system as a whole. So instead of this being 1, 2, 3, 4, 5 individual battery systems, the whole thing is one battery system. And that's only possible where there is the ability, in this case, we've got a BMS which is also controlling the whole string through comms. And so this system acts like one whole battery, even though it's made up of 5 battery modules. And therefore, even though each of these battery modules can source 100 amps, we're still listed or rated at 100 amps maximum output, because the string controller has got communication through here, and it can see what the current on every single battery module is, and can make sure that the current through all of the interconnecting cables stays within safe range. So if you're wondering why, for instance, when you look at the CEC approved module product list for batteries, just to give an example, because someone mentioned Pylontech, you'll see Pylontech are listed multiple times with 2 batteries plus controller, 3 batteries plus controller, 4 batteries plus controller, 5 batteries plus controller, because each one of those is a different pre-assembled battery system. And so they have to list them all individually. Shepsy says, Sherlock connectors normally have a 25mm crimp with the option to sleeve for 16mm. Yeah, so just be aware that you are doing something like this, not like this, when you're paralleling batteries together, because of that successive current increment. Okay, so let's go back to my slide. Where's my slide gone? Okay. So that's current carrying capacity. Now here's one that actually tripped me up, and have I got the right one up on screen? Yes, I have. This one tripped me up. So it's very easy to just assume that when you're putting together a system, hang on, have I gone the right slide? No, I haven't. Gone too far. Sorry, go back one. No, I've gone the wrong way. There we go. I've got it now. Geez, I'm having a few little self-tech problems. So this is a very popular combo, the Fronius Gen 24. This is the 10 kilowatt 3-phase, and the BYD. It's a stack. I think it's a 11 kilowatt hour stack of battery modules here, and the BYD battery has an output breaker rated at 63 amps. So what you've got to consider is that even though the Gen 24 may draw a maximum, say 50 amps, you've got to rate the cables for the output overcurrent protection device built into the battery. So because there's a 63 amp breaker there, we've got to follow the requirements for protecting a cable, or select a cable that will be protected by a 63 amp breaker. And so we had to go and find some high temperature rated cable. We used some Huber and Zuna, I think it was 110 degree rated, and we found that 10 mil could do the trick. So 10 mil cable, not a little bit of 6 mil. Often you'll find battery systems come with substandard cable sizes as standard. You need to confer with, or check with 388 that they are suitable for the application, and particularly when you consider derating. So in this case, this column is for cables enclosed in conduit touching a surface, which is pretty much what we've got there, and they rated a 10 mil cable flexible at 64 amps. So we just squeezed in with 1 amp to spare. So there you go. So make sure that you do your due diligence for cable selection based on the overcurrent protection device built into the battery system, and not just assume that the manufacturer has provided you with the right stuff. Do your due diligence. Okay, and now we're getting on to mechanical protection. Now this is yet another one that I was tripped up on. Kind of so used to just plugging PV into the bottom of an inverter. We know that 4777 part 1 says you can have 300 mils of mechanically unprotected cable at the PCE, as long as it's in a location unlikely to be damaged. And therefore, sort of the interpretation is that underneath the inverter is a kind of protected zone, and so flexible cable is commonly used to connect PV arrays into the inverter. But the wording for the battery system is, all cables that exit a pre-assembled battery system without overcurrent protection shall be mechanically protected by at least medium duty conduit up to the overcurrent protection device. Okay. And then it goes on to say, for battery systems operating at DVC B or C, and in this case, the picture I've shown is a battery system that's DVC C, the cables between the overcurrent protection device and the PCE shall be mechanically protected. Now, mechanically protected can be done in lots of ways. It doesn't automatically mean conduit. So we had to actually make a shroud. So if you look on the left-hand side, we made a shroud to go over the battery cables to provide mechanical protection as required in 5139. And it was my inspector who picked me up on that. So there you go. Inspectors know their shit. So you learn something every day. Shepsy, yes, I was using the 90-degree table because there isn't a 110. There's a 120 and a 90. But 90, if you can make it with 90, you can definitely make it with 110 degree rated cable. So yeah, you need to follow the work method in 388. And I should do probably a Toolbox Tech Talk on 388 because it's actually quite a complicated little standard. I used to think you just go to the table 4 because that's what I do, batteries. No, it's not that simple. And you've got to look at all the D ratings, not just within the means of installation, but also whether there is what the protection device is, whether it's a circuit breaker or a fuse, and there's D ratings based on that as well. So yeah, you've got to consider a few more factors. But anyway, that's a topic for another Toolbox Tech Talk, is how to read 3008. Okay, moving on. What are we up to here? So protection from overcurrent from the PCE. So you've got two sources. You've got the source of the batteries can source current into that cable, and the PCE can source current into that cable. And the overcurrent protection shall be installed on the pre-assembled battery system's DC port of the PCE. So at the inverter, so this is where you need overcurrent protection at the inverter, if the PCE charging current or load current under fault conditions is greater than the current carrying capacity of the conductor between the PCE and the battery system. And so when you read a standard that says and, both of these have to be true before you have to comply. And the length of the cable between the PCE and the battery system is greater than 3 meters. I should say the battery system's overcurrent protection device. So if there's more than 3 meter distance, that's when you need to have overcurrent protection at the PCE, at the inverter. If it's over 3 meters and it can source a higher current than the cable's rated for. So there you go. So it's another source. Thanks, Garth. Yes, AS3008 would be a good topic. So I think I've just flagged myself there for doing it next week. Yeah. So incidentally, some people ask me, like, why do I do this? Why do I spend my Sundays talking to you guys for free? You could say it encourages me to learn stuff. Because I have to teach this all the time. To keep yourself up to speed, you've got to keep reviewing what you think you know. And so every time I present or prepare for one of these things, I find something new in the standard that I didn't know before. Or in the case of my inspector, pointing out something to me that I didn't know before. So, I'm not perfect. I learn all the time. And so this is kind of a learning experience for me, and I hope you enjoy it too. All right, let's go on to the next one. And we're getting towards the tail end of my slides, I think. So what do we got here? Multiple isolation devices. Now, this was thrown at me straight away as soon as 5139 was published, and people saw pictures of the system that I have here at the lab. And it's got, in fact, I've only shown you one stack. We've now got 2 stacks. So we actually got 40 batteries all in parallel onto a power chain. And someone said, well, you're going to need a great big isolator for that whole system. But the standard actually gives you an out clause, and it says where you have, so you can have multiple isolation devices for the battery system. When a battery system has more than one isolation device installed, these shall be labeled. So by labeling, you can have many points of isolation. And so in this case, each of the circuit breakers on each of the Power Plus Energy batteries is effectively a isolator. It's also overcurrent protection. It's double poled, load breaking under fault, and therefore it's an isolator as well. but you have to specify that in the shutdown procedure. So it should say turn off isolators 1 to 20 to isolate this battery system. And you've also got to have that warning sign, warning multiple battery systems. Turn off all battery system isolators to isolate this system. So there we go. Now, if I come back to me, I think I've covered that one. I've covered this one. I'd had a few drawings that I'd done for you, and I think I've covered them all. Yeah, I have too. What do you know? I've caught up. So let's have a look at the chat, see if there's any questions in there just before we finish. So Jason points out paralleling is okay with the correct architecture. That's right, Jason. So you can parallel battery systems, you can parallel inverters, but you need to consider all of those requirements for isolation and overcurrent protection when you start paralleling. So it gets a bit more complicated. And Shipsy points out that solar cable is typically 120 degrees. Yep. You can use solar cable for battery systems, but if you're using like high currents, you probably won't be finding solar cable in the very large sizes, you know, over about 6 to 10 mil, and then you'll probably have to be using, effectively welding cable or something similar. Okay, so Shipsy's asking, maybe clarify for people voltage rating of DC breakers. Shipsy, that's actually a whole separate topic. It's actually in relation to DVC. Yeah, maybe you could give me a bit more information on that question, because I'm assuming you're thinking about the problems of non-separated inverters and how that affects the rating of any isolation device on the PV array side or the battery side, because of single fault paths through the PCE and using an MEN return path. But if it's something different, Shepsy, you probably have to let me know. While I'm waiting for Shepsy to fire back at me, anyone else got any questions they want to put into the chat? Now, I should check what my little slide notes say here. Okay. Oh, yeah. So just a reminder, I'm really happy to take questions via email. Don't try ringing me. I just really don't answer the phone anymore. Just don't have time. So, yeah, here's my email. And feel free to email me any questions. I get a few design queries too, like how do I design the system? I try my best to answer some of those, but boy, you guys have thrown some really curly ones at me. So, oh yes, Shepsy says the IP rating and our bugbear of IP23. Ah, right, I understand what you're talking about now, Shepsy. So Shepsy's referring to the fact that in 5139 we introduced a minimum IP rating of IP23 for isolation devices for a battery system, and for indoors, and IP56 if it's outdoor or in a weather exposed area. IP23 is higher than your standard HRC fuse switch. So HRC fuse switches are IP20, and so they don't cut the mustard. Now, this made a bit of a grumble when this was pointed out. People say, we've been using them for ages and there's nothing wrong with them. Well, there is kind of a few things wrong with them. From my experience, they are a very poor device. Expect a non-authorized worker to operate. I've had customers do things like rip them off the wall because it said operate quickly. They grab the handle and they pull it down past 45 degrees, break the hinge, and the whole thing comes off the wall, and now they've got no power. And to add insult to injury, the fuses drop out and shatter on the ground. So they're not a very user-friendly isolation device. They've also got a knife switch arrangement that is not really IP4X. You can put your fingers in there. And if you've got a DVC battery system, that's fatal. So, yeah, that's why we moved to IP23. And now we see the wide adoption of just using MCCB circuit breakers for high current battery systems, or just your normal circuit breakers for low current ones, and they do a perfectly good job. And I think Shepsy says, sorry, IP rating was a tack on to voltage rating, and yes, was in relation to non-isolated inverters. Shepsy, I'm going to save that for another Toolbox Tech Talk because I don't have to draw a whole bunch of stuff. But let me have a look. Oh, actually, I've got about 10 minutes left. Maybe I'll just do my best in the 10 minutes we have. I try to kind of keep this to an hour. And by the way, if you miss part of this, like came in late or you leave early, well, you wouldn't know about me saying this if you left early. It's available on my channel afterwards, so you can click on the same link again anytime. And a few of you may have noticed that I made a big boo-boo. I actually deleted. Excuse me. I deleted the scheduled live stream by accident, and so I had to reinstall it, and that gets a new URL, so I had to post out again to everyone the new link. So if you're wondering why the old one doesn't take you anywhere. So let me get my little drawing pad back in action again. Where are we? There it is. No, there it is here. And why can't I get it up? There we go. Overhead. And all right, so this is answering Shepsy's question about voltage rating of DC isolated. And I'm doing this kind of quickly. So I'm going to talk about a PV system as opposed to a battery system, just because this is the most common scenario that you'll see this problem occur. And so there's our, let's say 600 volt DC PV array, and it's connected to our PCE. Okay. And the PCE is non-separated. So the symbol for non-separated is just a single line. Double line means separated. So we've got our DC and our AC, and then of course we've got live, neutral. We'll have an MEN as our earth, so that's our MEN. Now, if this was a galvanically isolated PCE and it went faulty, short circuit internally, the fault current would be going basically around the circle, all around here. And that means when I switch off this ganged isolation device, both the positive and the negative poles are interrupted simultaneously, which actually means that the voltage of 600 volts is split evenly, 300 on this side and 300 on this side. So the switch doesn't actually have to do so much work because it's only breaking 300 volts at the fault current. But as soon as you have a non-separated inverter and you have a fault, say you have an earth fault, right? So a nice Australian possum made its way to New Zealand, chewed through some cables on the roof, shorted out to the array frame. You've now got a fault path that looks like this. Through the transformer, through the MEN, and back to here. You'll notice now that that's not true. It's actually 600 volts across one switched pole. And so suddenly moving from galvanically isolated PCE to galvanically isolated, from galvanically isolated to non-galvanically isolated, technically called non-separated, effectively doubles the voltage under fault conditions across the switchgear. And so therefore the rating goes up a lot. Now that's my real simple explanation, but we do have these I make, I break settings now in 5033. It was first introduced in Amendment 1 and 2 of the 2014 edition. It's in the latest one, 2021 as well. So that's where I'd have to go into a separate presentation to explain I make and I break. And I've got a feeling I've actually already done this in a previous Toolbox Tech Talk. So I might, Shepsy, suggest you go and have a look at some of those earlier ones. I think I've covered that already. And now Shepsy's saying, sorry, Glenn, I was talking about battery side another day. We'll try and chat via email. Yep, Shepsy, it does get a bit hard to understand sometimes when we've got just a bit of short text in chat to know what the full question is. But I think you've got onto something that I'd like to cover. So voltage rating of DC isolators and or overcurrent protection devices between a battery system and PCE. So that sounds all good. Yeah, okay. All right, so yeah, I think we've got to the top of the show, and the next Toolbox Tech Talk will be Sunday, the 2nd of March, same time, 1 p.m. Australian Eastern Daylight Saving Time. When Daylight Saving finishes, it'll still be 1 p.m., but it'll be whatever non-normal time. So yeah, that's my 1 p.m. gig. So thank you everyone for watching, and It's time for me to put the smoke machine on. And maybe play a few tunes.